All right, welcome to week 5, day 1. We are going to be talking about convex holes a little bit and debugging Bazookian's code here. So, code down here is commented out. I'm kind of rewriting it. So what you want to do when you're trying to find 2 points that are the furthest away from each other on a convex hole, doubly nested for loops is an easy way. There's better ways of doing this as well, but for the size of this assignment, it's no reason to be more complicated. So you just say for every point, try every other point, and just take the distance between them. So we're just going to grab point I, point J. If they're the same, we continue, so we ignore it. So I and J will not be the same, and technically you only have to go through, like, what? Half the... Yeah, it doesn't matter. You can optimize this quite a bit, but it doesn't matter. Okay, so let's get the distance between these 2 points. So the distance, double distance, is equal to the hypot function. It's the Pythagorean theorem. So it's the hypot between point 1 dot x minus point 2 dot x and point 1 dot y minus point 2 dot y. So that's the distance. If this distance is greater than our current best, which is c dot radius, then c dot radius is equal to distance. Okay, so at the end of this loop, that's it, actually. That's the whole thing. So, we should probably write down the center point too, right? So, c dot radius, no, not radius, c dot, was it center? Center and radius, yeah. So the center point is equal to the 1 dot x plus 2 dot x averaged together. And center y is equal to 1's y by 2's y averaged together. So basically what we're doing is finding the center point of a bounding sphere. The bounding sphere will wrap the entire hole. And the radius should not actually be the distance. The radius should actually be distance divided by 2. Right? But we can divide that out later. It's fine. So after we finish here, c dot radius divided by 2. Because if the distance is like 10 meters between 2 points, that's the diameter. Right? So the halfway point between them is going to be the center point, and then the radius is going to be half the diameter. CI does not name a type. Probably need to delete EU. Okay. So, see, created a bounding circle, and then the hole. Okay. And so we're going to see if the point is within the circle. If it's within the circle, you say it's outside? Okay. So that should return true if the point is within the bounding circle. Right, because the whole point is that, like, we don't want to do an expensive test if we can avoid it. So the whole reason why we create a bounding circle around it is we've got this convex hole. It's kind of irregularly shaped. And so what we're going to do is we're just going to wrap a circle around the whole thing. And if we do a point test and it's not within the circle, then we say it's outside the bounding circle. So this should be if it is not within the bounding circle, then you say nope. Otherwise, if it is within it, then you need to go through and do the cross product on all these things. It's inside the sphere, outside the hole. If any of them are positive, that is correct. And then you set true to false, and then, okay, you say it's within the hole. Okay. Yeah. Okay. So let's enter a point, 1, 1, 10, 1, 1, 10, 10, 10, 10. So we've got a square, and we're done now. Create a bounding circle, 5, 5, radius of 6.3. So that's the center point. And then we've got 4.5. Let's see if the radius is correct. So it's going to be 4.5 squared, doubled, square rooted, 6.36. Okay, good. That is correct. So now we're going to see if a point is within the hole. So let's try the center point. 5.5, 5.5. Does not print anything. Point is outside the bounding circle. Well, that is true. Okay. So why is it? So if it is, not within, that's correct. Foo equals true. For size I equals 0 is less than whole size. Why is it not printing anything? Break. Because you're not actually saying the other. Okay, so you're gonna need to debug this. Okay, your cross product isn't working right. Okay. So what you need to do is, for every point on the hole, you're going to create the point that you're testing on the inside. You create a vector from the starting point to the point, and then you have another vector from the starting point to the end, and you cross product those two things. And I'm not convinced you're doing that right on this one. Maybe you are, but that's your problem. But the bigger problem is, you can say here, else cout the point is inside the circle but outside the hole. There you go. So that'll get you going. You're gonna need to debug the cross product thing though. Okay. So that's good enough on that element. I'm not able to do grass entry on my map. You can't figure out the reason why. Okay, so if you want to share your screen, or I can just show you if you'd like on here. All right, if you watch stream, failed to load level start. Shinbi animations, what the heck is that? Level start montage. Interesting. Huh. All right. Let's see. Let's pop this out here. Okay. Full screen it. No, I don't want that. Nope. Just want that. I don't want the sidebar. No. All right, go ahead and speak. You're unmuted now.
Hello?
Yep. What's up, dude?
Okay, so I did add the grass in a layer, and every time I try to paint it, it's doing it, but it's not. Let me just make it bigger. So it should now populate grass. It's not populating grass.
Okay. All right, let's take a look at your landscape blueprint.
This.
Yeah.
Blueprint.
Sample grass, and you got a grass output node there. Zoom in on that part right there.
Here.
Yeah. So you're sampling the grass layer. And you have a grass output node. Click on the grass output node. Click on the brown part. There. Yeah. Okay. Open that thing up there.
This.
Yeah. Double click on that. Or yeah, there.
I imported grass in it.
Okay. 40 grass density. Start cool. Oh, you're start. Okay, never mind. Okay.
This I'm trying to scaling it. Maybe it was too small for it, but it didn't work again.
Right. Okay, let me see. Close out of that. Go back into the landscape. Blueprint. All right, where is your layer blend set up?
Layer?
Yeah, your layer blend. That's...
so the grass 1, and then I have grass 2 with dirt and going to the blend. And then in normal, it's the same thing, but without the texture.
Yeah, you need to use the layer. Here, let me show you what it looks like over here.
What do you mean by layer?
Let me show you. So, Bill, landscape material. So you need to have a layer blend node set up, and basically that allows you to paint grass on top of the thing. So that names the different layers. You can't do a layer sample like you're doing without having a layer blend node set up, and that's the automatic grass here.
Okay, so I need to add layer blend.
Yeah.
It's called layer blend.
Layer blend is a landscape layer blend, and then you create a name for each one of them. I have default, road, and meadow, and then after you do that, you have to go into your landscape and under paint, the different layers that you name there are going to show up now. And if they don't show up, then you have to put a different material on the landscape and then put your material back on the landscape so that it reloads. Otherwise, the layers don't.
In the beginning, it happened that with me on the grass when I was doing the grass, it didn't show up, and I did it with the material pre-uploaded and.
Okay, so after you do the landscape layer blend and you name them, they'll show up here. Do you see the little pluses here? You have to click on each one of those and just hit OK. Click on the plus, hit OK. Click on the plus, hit OK. And then after you do that, then you'll be able to spray point. You'll be able to come up in the landscape paint thing like this and spray paint, whatever.
Okay.
Like that. And then your landscape grass thing you can pick one of the layers or more of the layers. Let me show you. Right up here. So you can say, all right, so the meadow will generate grass automatically, and then you can actually add another thing here, and then you can have default feeding into that, and so you can have each of the different layers of your landscape generating different types of grass and stuff like that.
I see. When I was looking online for some kind of solution, I found somebody was doing a swamp.
Yeah. I
tried that too. Like I created the procedural foliage bumper, and the tree. I connected to it, but also I didn't swamp it.
Yeah. Again, if you're trying to do that without having your layer blend set up, it won't work.
So I need to work on the layer setup.
Yeah, you need to get that set up. Yeah, and if you check my IS50A playlist, I go through this like week 2, I think. I've got a couple lectures on the landscapes and how to do auto textures and all that kind of stuff. All right, cool.
And if you want to see where we are, like, the map is almost finished. This is the same map I used it in IS50A, and I'm upgrading in it.
Okay.
There's some writing stuff here.
Looks nice. Yeah. All right.
So it's like a fortress to hide from it.
Yeah.
But there's some AI coming into it too.
Sounds good. Yeah, in today's lecture in 50A, I talked about setting up a nav mesh and that kind of stuff. All right. Yeah, it looks good, man. All right.
Okay.
It's gone on Biddinghoven. All right, let's excommunication. Oh, that's why it's John Wick, I'm sure. That's funny. All right, so let's finish off. We're working on Friday, and then I'll just give you guys lab time. If any of you guys have any questions, feel free to ask. So what we've been working on is this, right? Like being able to render, rasterize a triangle. So where we finished, we're finding every point inside of the triangle that wasn't on the line. All the lines are being drawn, but the points inside are now just pluses. And so what we need to do is compute the barycentric coordinates. And so the barycentric coordinates are the ratio of the dot products, and so, or cross products, sorry. And so it tells you how close you are to, like if you've got one point that's red, one point that's green, one point that's blue, it'll tell you how close you are to each of those 3 points, and you can colorize it correspondingly. So, somehow the blue is appearing in the top left corner there. Maybe we can figure out why it's doing that. You see that? Right there? It's blue right there. Well, it shouldn't be. It's supposed to be the red pixel here. Okay. So we create 3 points. 10, 10, 10, 20, 20, 10. First point is red, second point is green, third point is blue. We turn these into a triangle. This is a very common approach for those of you in 50A watching this. Rather than having each triangle have a copy of all the pixel data, instead they just have a pointer into, well, it's an index, but it works like a pointer. It has a pointer into some giant buffer full of all the points. It says those are mine. So, Okay. Alright, so we're going to rasterize a triangle. So if they are inside of the triangle, we draw a plus. And instead of doing that, what we're going to do is do the barycentric coordinates. Alright, so we need dot product. And so we're going to dot product, and this is going to be useful for you, Bazookian, because it's exactly the same code you need to write. So if we have a point inside of the triangle, we need to cross product it with from one point to it, cross producted with the line, the edge, and that'll give you a number. And you do that for each of the 3 points, and then the color that you get out of it, it's going to be based on the proportions of the three cross products. Okay, so we need to take the vertex, the first vertex, which is, who's the first vertex? A. Is it just called A? Yeah, A is just the index into the vertex buffer. Is vertex buffer a global? It is. Okay. All right. Let me just use first, I guess. Okay. All right. So point whatever vertex is equal to, oh man, naming these things is tough. All right, so we want the first vertex. We need 3 vertices, right? I hate to do this, but vertices of the triangle, it's going to be equal to vertex buffer square bracket A, vertex buffer square bracket B, or I can use dot at either way. Vertex buffer square bracket C. So I'm going to copy out 3 points from the vertex buffer again. I really don't need to do this, but whatever. So I'm going to have the vertices vertex here. It's going to be 1, 2, and 3. And then I'm going to dot product 1 to the point that we're at with 1 to 2. Or cross product, though. Okay, so double, is it double? Int vector int cross products is equal to, no. So I don't like doing this, but cross products dot push back. All right, so we're going to cross product it now. All right, so it'll be auto cross p is equal to lambda. Didn't I already do this? Wait. Point. Do I have a line segment? Did I write a cross product? We have a point. Do we not have a cross product? Oh, there we go. Cross product. Okay, actually, yeah. Okay, cool. So we already have a cross product. Okay, so we don't need to do all this. Cross products is equal to first dot cross product with p. Oh, we've already done this. Okay, hang on. Yeah, cool. Never mind. We've already done all this work already. We got cross 1, cross 2, cross 3. Cool. All right, so now we just need to print the color should be the relative ratio of each one. So the sum double cross sum is equal to cross 1 plus cross 2 plus cross 3. Remember the barycentric coordinates. You're basically figuring out what the relative ratio are of the different triangles inside of the triangle. So we got our point P here, and so what we do is we cross product A and P with A and C, A and P with A and B, B to C with B to P to B. I'm saying that wrong, but yeah, B to P with B to C, and then you get 3 different numbers, right? And the 3 different numbers correspond roughly to well, they correspond exactly to twice the area of these different triangles here. And so if A is red, B is blue, and C is green, the amount of red you get is the relative size of this triangle. The amount of blue you get is the relative size of this triangle, and the amount of green you get is the relative size of this triangle. And so we just have to mix the colors based on the relative proportions. So can you explain it with a drawing? So do you see this, Bazykian? So if you cross product if you cross product C to A with what's it? C to B or something like that. Then that gives you the. Let's see. I haven't had enough sleep. I can't do this in my head. But it'll give you the size of twice this rectangle. And so cross product will tell you basically the size of twice each of these triangles' size for the opposite vertex. So what you do is you just add this. You add the sizes together, and then you can figure out what the relative ratio is. Like if this one size is 2, this one size is 3, and this one's size is 4. 2 plus 3 plus 4 is 7. And so 4 divided by 7, this would be 4/7 of it. This would be 2/7. This would be 3/7. And that's how much of the colors each one gets. Okay. So, all right. That's the sum, and then do they need to be absolute valued? If any of them are negative, we bail out. Okay, so I know it's going to be positive. And so what we do is, if any of them are negative, we bail. Okay, so then the color, let's see. Okay, so let's just turn them into ratios. Cross 1 divide equal to cross sum. So if cross 1 was 10, cross 2 was 20, and cross 3 was 30, the sum is 60. And so cross 1 is now going to be 1/6, cross 2 is going to be 2/6, and cross 3 is going to be 3/6. So these are now the relative convert to what percentage each cross product is, and then we're just going to multiply that by the color. So the unsigned int 8-bit red is going to be equal to cross 1 times, and we're probably going to get horrible rounding issues here, aren't we? Cross 1 times first dot r, first dot. Oh, it's a line segment. Dot start dot r, red. So what we had? RGB. Plus cross 2 times second dot. Oh, these are line segments, aren't they? Okay, so the line segment start index. Right. Okay, So we're getting the red value of the first point and multiplying it by what fraction it has. So if we're all the way near the first point and the first point's red, cross 1 will be 1, and it'll multiply it times 25500 and get 25500. Of course, it's going to round horribly, but whatever. And then we do the same for each of the 3 colors. Okay. Okay, so that adds together the red of the first point, the red of the second point, the red of the third point, based on how close we are to the different vertices. They will contribute based on how close they are. And we do the same for green, we do the same for blue, and then we set the background color to be red, comma blue, comma green. And yeah, sure. Print that, why not? Okay, let's see if that works. Hey, there we go. We got blue in the top left corner here. I think it might have been like when I flipped it, these colors went backwards, but yeah, it's so I kind of want to try this with a different triangle. So I'm swapping the starting and ending columns, but I'm not swapping the. Why do I get blue in the top left corner? That's the question. Why am I getting blue in the top left corner? These two are backwards here. That one's correct. Each of these guys is going to be different. Each of these guys is going to be a different point. The first point, no, we just guess. Now the top left corner is right. Okay. There we go. If I had more than 3 hours of sleep, I'd be able to tell you why that worked, but as it was. There we go. So let's try some other combinations, just so we're not completely... okay, in fact, let's make another triangle. I got these guys here, 1 through 5 lines of code. Alright, so, and we'll have them maybe even overlap a little bit. Maybe 15, 10, and let's see, 15 down, 10 across. Then we'll go to like 5 down, 20 across. And then like 10 down, 10 across. And if that's not, oops. Yeah. Try 2. 3, 4, 5. There we go. All right. So we've got 2 overlapping triangles now. And they just, the second one just overwrites over the first one. And so in early 3D, this is actually how they did it. Is this code in public? I can put it in public if you want. Copy main.cc into public rasterize.cc. So it's in /public/rasterize.cc. And so back in the day, they thought memory was actually very expensive back in the day. It was actually, there's a trade-off where they would actually use more CPU time in order to save on RAM costs, because RAM was like $1,000 a K. So if you're going to be trying to do graphics, which consume a lot of memory, you do everything you can to keep the memory under control. That was, of course, the olden times. Nowadays, memory is very cheap, and so we use memory to speed up CPU things. It's much less of a trade-off these days, So they use something called the painter's algorithm. And so the painter's algorithm would, if you have multiple overlapping objects, like a demon standing in front of a wall, what it would do is it would paint the wall first, and then it would paint the demon over it. And that's why it's called the painter's algorithm. If you want to do a red square on a white background, you do the white first, then you draw the red square over it. And that way you don't need to do what's called ZBuffering. However, we can do ZBuffering. So ZBuffering is how far away each of these points are away from the screen. So what we need to do is set up a ZBuffer, which is a 2D array holding the depth at each point. And when we rasterize, we only draw if we're closer than any of the points in there currently. So let's do that. Let's come up to the top. We'll just make it a global because we're using all of the worst coding practices, I guess. So we will make this doubles, I guess. A vector of doubles named ZBuffer. And it's going to be a vector of vector of doubles. And yeah, so it's going to start off of size 0. So after we actually we don't, do we need it up here? Yeah, we do. Yeah, we need it up there. So the first time we start up, we're going to need to get the terminal size and hope that the resolution doesn't change. That would be quite awkward. All right, so then we will resize for every for int I equals rows, print I equals 0, I is less than rows, I plus plus. We're gonna make the ZBuffer make the ZBuffer rows times columns in size. So for basically every point on the screen, we're gonna make a double for it, and that will hold how far away the point is. And if it's 0, that means there's nothing drawn there, and we can draw there. Or we can fill it with max values, and so anything you draw will be in front of that. Yeah, either way. Getting a max double is a little bit weird. Limits max double. Numeric limits max for double max. Okay. It's in C limits. Is it? Is that where it's found? All right, you okay with that? All right, thank you. All right, so we will just initialize the ZBuffer, and I guess we can only rasterize once without clearing it, maybe. Yeah. Now let's make a function for that, so we can every time we're going to draw a new frame, call this function to the ZBuffer. Okay. Void clear ZBuffer. Okay. So for every one of those, okay. ZBuffer dot resize to be the number of rows. So that'll create a number of vectors of doubles, and then we have to go through each vector of doubles and resize them out to be the number of columns. So for int I equals 0, I is less than rows, I plus plus, ZBuffer dot square bracket I is fine. Okay. Either way. Dot resize to be calls. Passing in numeric limits angle bracket double dot colon max. See if it likes that. So what we're going to do is we're going to resize it to be size, 60 or whatever, and then each value is going to have the max value of doubles in there. And that way, any distance we come up with from the screen will be smaller than the max distance, which is some ungodly large number. Okay. Okay, so that will initialize the ZBuffer. And then when we rasterize, what we're going to do is, in addition to the color, which is going to go into this, well, we should have a ScreenBuffer as well. But, yeah, whatever. We'll just use the terminal for it. What we're going to do is we're going to write how far away each point is. And right now, the points don't have a depth. So let's add that. So every point now has a Z value, which is how far it is away from the camera. These are in screen coordinates. So rather than it being an X, Y, and Z in the world, which we're projecting onto the screen, we're just starting with everything already projected onto the screen. So everything's just in terms of rows, columns, and then how far away it is from the camera. Do you guys understand what I mean by screen coordinates? Buzikian, Binninghoven, Singh versus world coordinates. World coordinate might be at like 30,000 meters away from the origin or whatever, and our camera's looking at it, and what you have to do is you have to project the object in the world onto the screen, and you get like the pixels you're going to draw. And so that would be the next homework assignment if I was having you guys do this. Yeah, it's like reading maps, so it's all 2D. And so you have, a row, a column, and then how far it is away. So it's like an orthogonal projection. How does this work in 2D? Like knowing depth. Well, in 2D you can have, like in Mario Brothers, you can have a background, and then you can have things drawn over the background. And so you can draw a rectangle that's far away, and you can draw a rectangle closer, and the closer rectangle will draw over it because it has a near Z distance. Z is how far it is from the camera. So, the bigger the number, the further it is away, the less likely it is to get drawn if it's overdrawn. Okay, well, to do add depth to each point, that's done. Okay, so we'll do U to hs.z. And if we output it, So we now need to add a depth to it. I guess the first triangle is going to be at depth of 1. So it's going to be pretty close. And the second triangle will be at a depth of 2. It'll be further behind. And so we need to do ZBuffer, whatever function was called, clear underscore ZBuffer. Okay. Clear ZBuffer. So we're going to initialize the ZBuffer. It'll, will it do that? If we resize it and it's already the size, we might do ZBuffer dot empty, clear. So we'll throw away the existing ZBuffer and then make a new one. Okay, so then the only change we need to make here is that when we rasterize, we just need to check to see if the ZBuffer has something in it already. All right, so line segments. Okay. So in addition to lerping the RGB values, we need to lerp the Z as well. Actually, that shouldn't be an int. It should be a double. Yeah. Okay. So when we draw a line, we need to say double Z. So we're just going to lerp between the starting Z. Starting Z? Start Z. What is start? Start is a point. Points have Z's in them. Okay, starting Z to ending Z. And double... simplify this. Double alpha is equal to double I divided by horizontal distance. There. And so if one point has a high Z value and one has a low Z value, then as you go along the line, it'll smoothly interpolate between the two. And this way we don't have to do the division every time. The optimizer would probably pick that up, but it's also less typing overall to read. Okay. Then we'll need to do the same for this one. Double alpha equals 5s vert. QQ D $ append alpha close parentheses semicolon escape B down Q off at Q there we go YYP Z. Okay. We're currently not doing any Z testing yet, so let's just verify that this is still going to render properly good. Okay. So now we need to do a Z test. So we're not going to actually draw the thing unless we are the nearest thing. So we are going to check the Z value there. So double buffered Z at this location is equal to ZBuffer dot at row dot at column. See what depth is already there. And if we're closer, right? So if we've just drawn a triangle like 50 meters away, we're about to draw a triangle 10 meters away, we're closer than it. But if we're going to draw something 100 meters away, it'll be occluded, right? So only draw if we're closer. So if our z is less than buffered z, and you might ask, should it be less than or equal to? Doesn't really matter. It's floats. So if z is less than buffered z, then, and only then, draw the stuff. Oops. And also set the ZBuffer to be and then we write into the ZBuffer the distance of the pixel that we just drew. Okay. And then we just do the same for the other. Mark x, y, single quote x. And now only the nearer thing should draw for the line segments at least. There we go. So you can see right here the nearest segment is drawing over that segment back there. Maybe we'll have the second triangle be a little bit to the left. So rather than starting at column 10, let's have it start at column, let's see, row, column. Let's have this be like 7. Move it down a little bit. There you go. So you can see this is overdrawing it. All right. So now we need to do the same for the center, all the center pixels. So, all right. So that's the red, that's the green, that's the blue, and then we'll just do the same for the double Z, as the Brits say. So it's going to be y3y, paste, y3y, paste. So first dot start index dot b dot z. Okay, so that is going to be the barycentric coordinates of the z depth of it. Since all of our z depths are flat right now, 1, 1, 1, 2, 2, 2, it'll just be, hopefully, 1 or 2. Since we're using doubles, it should be fine. Shouldn't get any rounding issues on this that are significant. Alright, and then, so now that we've figured out how far away that point is, do you guys understand this part here? Like what we're doing with it? We sum up the cross products, and then we figure out what proportion, like if you add 10 and 10 and 20, it's going to be a quarter, and a half. And so we're just saying what the relative ratios of the different cross products are. Okay. And then that controls how much red you get from one point, how much red you get from the other point, how much red you get from the other point. It's just the point opposite. It's just, yeah, you just blend them together. So, yeah, so now we just need to do this here. I need that. Okay, so did we take that one out? Do we have a move cursor in here somewhere? Yeah, okay, we do. Actually, we don't need to move the cursor unless we're actually going to draw anything, so let's put that in there instead. Right, minor optimization. Okay, and then when we're drawing the triangle, if each point that we're trying to draw is closer than the one we have in there right now, we move to the spot and we write to the ZBuffer our depth so that, you know, if somebody comes in closer, it can override it. If they're further away, we'll include them. Background color and that. Okay. There we go. So you can see that this first triangle here is just entirely blocking the rear triangle. Okay, so even though the second triangle back here is being drawn second, because the first triangle is nearer to the camera than the second triangle, it is completely blocking off the rear one. And so if we wanted, we could add animations to this. We could clear the screen and move the triangles around and have like a triangle rotate or something like that. But I think that's good enough for today. So we've got Z-buffering, so we can draw multiple triangles on top of each other, and maybe we can, I don't know, 5, 5, 20, 20, and 12, no, let's see, 5, 10, and right a little bit maybe. I think it might be we're drawn in the wrong direction. Yeah, it's not drawing anything on the inside. Let's move it. 15. There you go. So you can see this triangle back here is just getting blocked by the front triangle. Right? So make them a little bit bigger maybe. There you go. So kind of a beautiful gradient we got going on. Let's see. Colors don't match again. Whatever. Okay, so if you want, we could add rotations in, animations, and you know, have world to screen coordinate projections. But like I said, this is probably a good spot to stop for today. So keep working on your projects, and I will see you guys tomorrow. All right, peace out.